Hello. In this assignment, our main goal was to create and train a deep learning model for image classification using the CFAR-10 dataset. And in this assignment, we loaded the CFAR-10 dataset and pre-processed the data, and then we implemented the k-fold cross-validation. We used two folds. Um, Originally should be five, but unfortunately it was taking too long to process, so we decided to lower the um, faults, and we built a convolutional neural network. Then we compiled the model by using Atom Optimizer. um, we used the categorical cross entropy for loss, and our metric was accuracy. We used we applied data augmentation uh, using Keras image data generator. We trained our model with early stopping, so it would monitor validation loss, and it would stop the training if the loss does not improve for 10 consecutive epochs. Um, we repeated the model building, training, and validation process for each fold. Then we averaged the training histories across all the folds. We evaluated the final model on the test set, and then we did some plotting on our training history. First, we are importing the libraries that we need, and after that we're loading the CFAR-10 dataset. We're saving it into train images, train labels, test images, and test labels. uh, then we are normalizing the images. We're dividing it by 255, and then we're saving them into one hot encode uh, the labels, and using two categorical that converts a class of vectors into binary class matrix. Then over here we have our k-fold cross validation. The variable is set to 2. That means the dataset will be split into two parts for cross validation. And then over here, stratified k-fold is used to create two stratified folds, and it ensures that each fold has a similar distribution of class labels. And then over at the for loop, it iterates through the two folds. For each fold, the training and validation indices are obtained. Then inside the loop, we have x train fold and x value fold. These are for training and validation images. And then in the meantime, y train fold and y value fold are the corresponding one hot encoded labels. Then we move on to building our model inside the for loop. A convolutional neural network model is built. It has three convolutional blocks, and it's followed by a fully connected layer and a final output layer with 10 nodes, one for each class. The model uses batch normalization and dropout layers to improve generalization. We have our dropouts here, and then batch normalization. We also used max polling 2D as well. The model is also um, compiled using the Atom optimizer with a learning rate of 1e minus 4 and categorical cross entropy for loss. And our matrix is accuracy. The learning rate is a hyperparameter, and it allows and it controls how much the model's weights are updated during the training. A smaller learning rate means slower but potentially more precise results, while a larger rate leads to faster results but maybe uh, overshoot the optimal solution. And set the rate to 1e minus 4, which is 0.0001, and it's a commonly used value for the learning rate in deep learning, because it provides a good balance between the speed of uh, convergence and the precision of the learned rates. And over here we have our data augmentation. The data augmentation is applied to the training images by using image data generator, and it helps improve the model's generalization by generating new training examples through random transformations, such as rotated, shifting in range, and flipping. And then we move on to the training. We train the model using 64 batches and 50 epochs. And early stopping is used as a callback, and stopping the training if the validation loss does not improve for 10 consecutive epochs. And the trained model's history is stored in the histories list. In summary, the code performs twofold cross-validation on a convolutional neural network using the CFAR-10 dataset. It has data augmentation and early stopping. And this is how the epochs looks like. Starts with a very low accuracy and a high value of loss, and by each epoch it gets better, and by the end result we get like accuracy around 0.7 and the loss is 0.8. Initially I was running this at 100 epochs, but it was taking too long for us and it was creating problems, such as we've used uh, usage limits in Colab, and it was either taking too long or it was asking us to pay, so we had to switch it to 50, and we had to switch the um, faults to 2. Moreover, moving on to the averaging the histories. So it's an empty dictionary. It stores the average history values for each metric, such as accuracy loss, validation accuracy, and validation loss. And then the for loop iterates over the keys in the history object of the first fold. These keys represents the different metrics tracked during the training, such as accuracy loss. And inside the loop, for each metric, the corresponding values from all the folds that was stored in the histories list are retrieved and average along the first axis, which is 0. This results in um, the average value for each epoch for the given metric. And moving on, we evaluate the model on the test set, and we get a test accuracy of zero point 0.7. And then we plot the average training history, and this is what it looks like. We can see that the training accuracy increases over time, and validation accuracy also improves along with it. And we can see how the training and validation loss decreases over time. We can see the loss on the left side and epochs on the bottom, and we can see the accuracy on the left side and the epochs on the bottom. Moving on, we can also see the smoother training loss and dashed lines. We can see that over here, smoother train accuracy and validation accuracy almost goes parallel to each other, getting very similar, getting very close to each other at the end. And over here, we can see how the smoother train loss uh, and smoothed validation loss over here, and we can see that how smoothed validation loss crosses over the smoothed training loss. And over here, uh, we can see the same graph, but this time we filled in the graphs, and we can see that this represents the overfitting and underfitting in our models. So these are the times where there were overfitting and underfitting, and same as our training and validation loss. And this is pretty much it. I want to thank Josiah, Raukirat, and Edward for their contribution. It was a great learning um, metrics for us, and thanks for listening.